Hello everyone, I'm Runjia.
I'm Yujie.
Today we are presenting our technical paper, Performance-Based Midsole Design using Computational Multi-Objective Optimization. Additive manufacturing, also known as 3D printing, has been broadly applied to product prototyping and fabrication. With the advancement of data science and volumetric modeling toolkits, there are opportunities in the footwear industry to employ computationally generated lattice system in place of conventional components and materials in order to enhance performance with new design possibilities. Located between the upper and the outsole, the midsole performs as the main cushioning, stability, and pronation control component. Midsole materials, subcomponents, and overall composition determines the quality of the running experience. And thus many running shoes end up featuring a broad range of midsole components and materials. Data-driven computational design offers opportunity for personalization.
There have been many explorations of underfoot pressure data as the primary form factor. In recent years, New Balance partnered with Nervo Systems to develop 3D printed midsoles for performance running shoes, in which the 3D printed lattice geometry was determined by pressure data. The project presented below challenged this conventional footwear data usage by proposing a new design agenda that treats ARAMIS data as the primary factor and pressure data as the secondary factor. We see an opportunity to add on to this data-driven approach through taking the temporal implications of running into consideration. Various parts of the midsole come into effect during various stages of human movement, and this can be used to inform lattice distribution and structural units design.
Methodologies. The project uses a synthetic workflow of ideation, data-driven design, and multi-objective optimization. The ideation process composed of two hypotheses about the project. The first one is a hypothesis about system global performance and data type of interest. The second hypothesis is about the unit local performance and quantitative properties. The data-driven design approach is composed of data acquisition, deep temporal data clustering, midsole segmentation, and unit choice. The outcome of the data-driven design approach serves as the input for the multi-objective optimization step, which composed of design space exploration, performance simulation, prototyping and fabrication, and segment blending. The first approach for data-driven design is the data acquisition. The performance-based midsole design starts with the ideating how available data types affect the running experience. There are two types of footwear data, both obtained from New Balance in this project: the underfoot pressure data and the ARAMIS data. The ARAMIS data reflects the load distribution and the surface deformation in the running process. And due to its sequential nature, it makes it possible for us to track the midsole's behavior over a specific time span. And after the data acquisition, we apply deep temporal clustering to help us analyze and understand the behavior of different zones of the midsole and comes up with different data interpretations to inform various types of design. We apply the deep temporal clustering algorithm for the data clustering and used the K-shape clustering algorithm for determining the optimal numbers of clusters for the project. After a series of analysis, we discovered the optimal clustering to be 6. With 100 frames of displacement as strings, the data was first segmented into 4-8 clusters, depending on their string temporal pattern, calculated by the K-shape algorithm. And the optimal number of cluster 6 is selected with validation. And then we took the 6 optimal zones and tested them with various proposed optimal lattice units to be distributed in each segment. Various lattice units were picked to suit the temporal pattern, ranging from an auxetic structure that provides cushioning and bouncing to a solid minimal surface shell structure that provides resistance in the pronation process.
In our computational multi-objective optimization phase, design space exploration approaches the agenda by making iterations with selected design variables. We control form factors of the lattice system and focus on performance of the lattice unit with two variables: the internal form factor, which is the scale ratio for compactness, and member diameter for the sake of manufacturing feasibility. Performance simulation approaches the agenda by setting up multiple optimization objectives and searching for optimal unit cell design. We treat auxetic units as beam-like structures and gyroid units as shell-like structures. Finite element analysis is implemented here to quantify displacement of members of the lattice units when being applied to the same load. Prototyping and fabrication approaches the agenda through making one-to-one partial prototype with recent 3D printing. This helps understand actual material performance and behavior through physical impressions and simple material tests. Segment blending creates a smooth transition between segments by tuning material density and blending the unit cell structure. The blending factors are associated with the characteristics of adjacent segments.
Results and discussion. The Midsole design used a lattice system as a flexible structure, as this structure could be easily deformed and remapped. A variety of lattice units were tested, starting from the auxetic structure with various form structure and member diameter that provides cushioning and bouncing, to the solid minimal surface structure of various mathematical expressions that provides resistance in the pronation process. We have developed multiple design outcomes and evaluated them based on our metrics. After multiple rounds of iterations, we choose the design with the best performance as well as the best aesthetic quality.
Unlike the common approach in which certain types of lattice get distributed across the midsole according to an averaged pressure data, we start from ARAMIS data and leverage various computational optimization tools to enhance design decisions. The temporal clustering methods provide insight into how material responds to various stages of running. The multi-objective optimization quantifies metrics for design space exploration, and performance simulation helps create evaluation metrics and compare various designs. While computational optimization tools become central in decision-making processes, human interventions become even more crucial for setting and running such systems in efficient and intuitive ways. We're witnessing the challenges of blending visual and performative design goals in this project. We find that subjective decision-making, such as visual choices, cannot easily be quantified. Yet still, such decisions remain significant for design exploration. This is the end of our presentation. We want to express our gratitude to Onur, MIT Department of Architecture, and New Balance R&D Innovation Studio for the generous support of this project. Thank you for your time.